Assalamu alaikum. My name is Nجود. Today I will be talking about renewable energy and to be specific, wind turbines. So first we have wind turbine types. We have two types. We have horizontal axis and vertical axis. What do I mean by that? Is that horizontal axis, it's horizontal shaft actually. We have single to many blades, 2 to 3, which is more efficient, and to be more detailed, 2 is the most efficient compared to 3 blades. We have upwind and downwind facing. Upwind and downwind facing means that the horizontal blades could collect the wind from the front or the back, both sides. We have solidity, aspect ratio, speed and torque. We have shredded duct, diffuser, augmented, wind turbines. These are the types. For the vertical axis or vertical shaft, we have Darius, which is lift force driven, and we have Savonius, drag force driven. What do I mean by lift force? Is that pressure difference is required. So how it works is that when a blade has like high pressure and low pressure, it allows the blades to rotate, and that's the clear example of the lift force driven. For the drag force, simply it's just a blade that collects wind and just rotates. That's it. No pressure difference needed. So these are the two clear examples of drag force turbines. This kind, actually, it's a mix between both lift and drag force, because basically it's vertical axis. It requires no horizontal wind. It could rotate just it could easily just rotate vertically, okay. And its blades kinda it's actually designed a bit to have some sort of two pressure needed blades in order for it to rotate more. So these are the two types. So moving on to wind turbine subsystems. Here we could compare between the horizontal and vertical axis turbines. We have first the rotor diameter here. For the horizontal axis, we have it like this, and for the vertical axis, we have it here, like this. Okay, we have gearbox, we have generator, we have the nacelle. The nacelle actually it holds the gearbox and the generator. We have the tower, we have obviously the foundation. And the vertical axis turbine, we have the generator and the gearbox at the bottom, okay. And here are the fixed pitch rotor blades. And here we have the rotor height, okay. So going back to horizontal axis turbine, here we have the rotor that holds the blades together, okay. Here is one blade, and actually we can see that it's not designed to be just rectangular shape. It's kind of like it has some kind of shape here, and this allows to have a pressure difference actually in order for the blade to rotate. We have here a blade pitch, we have the low speed shaft, and here is the high speed shaft. of course, it's connected to a small gear, the high-speed shaft I'm talking about. We have the gears, the gearbox actually. We have the generator, we have a controller, we have the nacelle that holds everything. It's a housing for everything. We have wind vane that tells us where the wind is heading, or the direction, or yeah. And we have the brakes. We have the yaw drive. We have the yaw motor. Actually, the yaw, it's the part where the whole turbine rotates, or like when we have different wind direction or something. That's the mechanism that rotates it. We have yaw motors to give power to rotate the turbine. We have the tower that's holding the turbine. Foundations and tower. Evolution from truss early 1970s to monopole towers. So here, before the design that was generally used was the truss, but in the early 1970s they developed it to be on a monopole towers. So here we have many different configurations proposed actually for offshore, with different depths, with different mechanism used. Actually, some kinds are proposed actually to be floating, some kinds are proposed to be tripod fixed bottom with a different depths. Yeah, we have here actually we're going to talk about the nacelle and rotor and hub. Main rotor design method in ideal case. So when we're trying to design, we have some configurations we should consider or to follow. There are basic configurations. First, orientation and blade number. We should decide how many blades we're gonna work with, and what is the configuration, like what type or what's the shape. Is it vertical axis? Is it horizontal axis? When we decide all that, we go to step 2, which we take a site, wind speed and desired power output. We go out there and we visit the site where the turbines is going to be put at, and we just we see like what is the power output we desired to take a decision. Third, calculate rotor diameter, accounting for efficiency losses. So we should consider rotor diameter because we're gonna have to have an output. We have to check the efficiency. We have to see the efficiency losses we're gonna lose, or what is the structure is going to take before we have an output. Then we have to select tip speed ratio. Okay, the higher, the more complex airfoils and noise, of course, and the blade number, the higher the blades number, the higher the blade number, we will have a higher efficiency with more blades. So more blades, more efficiency. Okay. Then we will have to design a blade including an angle of attack, lift and drag characteristics. So we're gonna design blades, okay, that has an angle of attack. Actually, an angle of attack, it's the angle at which the chord of a blade of a turbine meets with the relative wind. So it's an angle that deals with the wind. I mean, it's an angle of attack, we call it. Okay. And last, we have to combine with theory or empirical methods to determine optimum blade shape. Now talking about wind turbine blades, we have blade tip speed, we have pitch control, we have two blade systems and hub. Okay, what is a pitch control? Okay, it's actually this part where it holds the blades, okay, and we should have a control of it to have the best angle to collect wind. Here, the blade tip speed, actually we can't say just a blade speed, but we have to have a tip speed. And the tip speed actually to know what is the RPM, the output of the RPM. Like it has a relation with the diameter of the blade and the omega. So to know what is the output of the RPM. And the two blade system and the hub of the turbine. So electrical generator. Actually here we have rotating magnetic field induces current. This works with while a magnet rotating, while it's rotating, it could induce a current. That's how we could get actually electricity also. It's a generator as well. We have the synchronous permanent magnet generator, potential use without gearbox, and it's historically higher cost use of rare earth metals. And we have the asynchronous induction generator, slip operation above or below, synchronous speed possible. It also reduces gearbox wear. We have the control systems and electronics. We have the drivetrain speed, it's fixed, direct grid connections and variable power electronics for indirect grid connection, blade regulation stall, blade position fixed, angle of attack increases with wind speed until stall occurs behind blade. So what is stall? It's actually a point where turbine cannot rotate more, even though sometimes we have a lot of wind speed, but turbines won't move. That's a point where we call it a stall. Okay, and we have pitch blade position changes with wind speed to actively control low speed shaft for a more clean power curve. Okay, basically, as I said, as I mentioned, what the pitch actually is, it's actually to control the blades, and we could actually reduce the speed of the blades where we have a lot of wind. Wind grid integration, short-term inflections and forecast error, potential solutions undergoing research. The wind grid integration, it's to collect actually electricity from turbines and put them in the grid. يعني نجمع electricity من wind turbine and we put them في الشبكة الكهربائية حق المدينة يعني حق المكان. Future technology development. If we would like to improve the performance, we can control the capacity or the capacity factor. The capacity is by higher heights. We could put turbines in higher heights. We could use larger blades. We could include superconducting magnets. We could use advanced control methods, individual pitch and smart blades, site-specific designs. We could reduce costs by weight reductions, two-blade designs, advanced materials, direct drive systems, and offshore wind foundation, construction and maintenance. Future technology development, improving reliability and availability. We could improve reliability and availability by forecasting tools and dealing with system loads. Advanced control methods, materials, preemptive diagnostics and maintenance, direct drive, complete removal of gearbox. We have some kind of turbine designs which won actually the Nobel Prize. It's shrouded, floating, direct drive and high altitude concepts. These are the designs. Actually, they are so modern looking. So moving on to lecture 3, we have historical development. Wind has been used by people over 3,000 years for mainly grinding grain, sailboats and pumping water. We have here the Babylonian emperor planned to use wind power for his ambitious irrigation project during the 7th century. We have also the wind wheel of the Greek engineer. It was using a wind-driven wheel to power a machine. That was their technique. We have here, by the 13th century, grain grinding mills were popular in most of Europe. So that's a picture of the old windmill that they used to have. The era of wind electric generators began close to the 19th. The first modern wind turbine, specially designed for electricity generations, was constructed in Denmark in 1890s. The first utility-scale system was installed in Russia in 1931. A significant development in a large-scale systems was the 1,250 kilowatt turbine fabricated by Palmer Buttman. Here we have some pictures built around a central post. Very old actually pictures. Here we have some information about the old windmill that they used to have. So that's a picture actually that was taken on 1941 in Vermont. This used to produce 1.25 megawatt with a height of 53 meters, and that was the largest turbine for 40 years. Structural steel, as we can see, and this turbine actually lost a blade in 1945. That's more pictures of the horizontal axis wind turbine and a vertical axis wind turbine, a Darius type. Current status and future prospects. Wind is the world's fastest growing energy source today. We will see it later that it's true that in the early years we saw actually that there are some facts, there are some studies that have been made. So the global wind power capacity increases at least 40% every year. That's a huge increase. For example, the Europe Union targets to meet 25% of their demand from renewable by 2012. In Spain, wind energy resources contribute 53% of the total generation of the electricity, which is something very huge, that they are relying on renewable energy and wind turbines. So installed capacity may reach a level of 1.2 million megawatt by 2020. Here we have the global wind power cumulative capacity, and we can see the development actually. The wind power worldwide in June 2010. Here we have USA with 36,300 megawatt, which is the most. Of course, considering how large the country is. Second, we have China with 33,800 megawatt. Moving forward, we have the evolution of commercial US wind technology. As we can see, in 1980, we used to have a turbine with a truss, and it could it used to actually produce 50 to 300 kilowatt with a diameter of 5 meters to 3 meters. This means that between the blades, if we connected them and we made a circle, like the diameter 5 meters to 30 diameter, used to produce 50 to 300 kilowatt. Okay, here are some descriptions. They used to have a 3-bladed upwind yaw driven, constant speed and 2-speed, stall regulated tip brakes or full span pitch controlled, fiberglass blades, geared transmission, induction generator, steel truss or tube tower. Here between 1990 and 2000, we had a better looking actually with a more efficient outcome turbine that had structurally stiff 3-bladed upwind yaw driven, variable speed and constant speed, special airfoils, stall regulated and pitch controlled, planetary transmission, induction generator, large size to reduce COE. Here we have them producing 300 kilowatt to 750 kilowatt with a diameter of 30 meters to 50 meters. Here between 2000 and 2010, and it's the future innovation, scale to large size, advanced blade materials and manufacturing, low speed direct drive generators, custom power, electronics, high efficiency, feedback control of drivetrain and rotor loads, more flexible structurally, O&M reduction features. Here we also see, we could see the development, past and present wind turbine. We can see actually, and we can say that they used to produce 75 and only 75 kilowatt. Nowadays they can produce 20,000 kilowatt with a height of 250 meters. Okay, moving on. We have types of wind turbine generators. We have one blade, we have two blades, three blades, multi-blade. Here we have upwind passive yaw with tail vane. If we have a wind going this way and the turbine is facing the wind, we call it upwind. Here we have upwind passive yaw with fan tail, with a fan tail. Here we have upwind active yaw. Active yaw, it means that we have a yaw with a controller that sends signal to the yaw to turn if we had to, I mean. Here we have downwind passive yaw with coning. Vertical axis wind turbine, we have H and delta, diamond, Y and phi. Here are some clear image of the vertical axis and the horizontal axis. Here are some advantages of vertical axis turbines. It accepts wind from any angle, ease of service, lighter weight towers, can theoretically use less materials to capture the same amount of wind. The disadvantages are rotors generally near ground where wind poorer. يعني احنا the more we go higher the more wind we get. بس يعني when we have turbines at the ground level we have poor wind. We have poor self-starting capabilities, requires support at top of turbine rotor, requires entire rotor to be removed to replace bearings. Poor performance, reliability, less efficient, have never been commercially successful on a large scale. Here we have horizontal axis wind turbines. Rotors are usually upwind of tower. Some machines have downwind rotors, but only commercially available ones are small turbines, proven viable technology. Here we can compare between horizontal and vertical wind turbines. The output power, horizontal axis gives wide range, but vertical a narrow range. Starting the horizontal axis turbine, it's a self-starting, but compared to a vertical axis turbine, it needs like a push or something, so it needs starting means. Of course, efficiency, the horizontal is higher than the vertical wind turbine. The horizontal is lower, the price is lower. Vertical axis turbines is higher. Wind direction, for the horizontal it needs redirected when the wind changes its direction, but the vertical axis turbines does not need redirection into the wind direction, because here for the horizontal axis turbines we have actually wind vane to send to the controller and then to the yaw and then to rotate the turbine, but here it does not need redirection. Generator and gearbox. In the horizontal turbine, it's at the top of the tower. In the vertical axis, it's at the ground level. Maintenance, it's difficult. Here it's easy, in the vertical. Upwind and downwind. In upwind, wind is facing the front of the wind, but downwind is facing the back of the turbine. Upwind turbines have the rotor facing the wind as shown. For the following features, avoid the wind shade that the tower causes, which improve the power quality. Fewer fluctuations in the power output, requires a rigid hub. This is the dominant design for most wind turbines in the megawatt range. For the downwind, rotor can be more flexible, increased fluctuations in wind power, only small wind turbines. Here we can see the relation between tip speed ratio and rotor power coefficient. For example, here we have one blade turbine. As we can see that at the tip speed ratio, it has the most wide range of tip speed ratio, but it's the least in power coefficient compared to two blades. It has less tip speed ratio range, but it has more actually power coefficient. 4 blades, it has a very narrow tip speed ratio range, but it's the most efficient. So the more blades we have, the narrow tip speed ratio, the more efficient power coefficient we could have. That's a photo of a single blade turbine. Sizes and applications. For the small turbines, it produces less than or equal to 10 kilowatt. That's used for homes, farms and remote applications. Intermediate turbines, it's 10 to 250 kilowatt village power, hybrid systems and distributed power. And here we have large, and it's 660 kilowatt to 2 or more than 2 megawatt. It's used for central station wind farms and distributed power and community wind.